Assalamu alaikum students, hope you are doing well. Let us start part number 2 of chapter number 13. Topic of today is induced EMF. Students, you have heard this word EMF, that stands for electromotive force. But let us understand today what does the EMF means. Students, have you ever understood why when bulb is connected with the battery it is lightened up? What force is behind that is driving that bulb to be lightened up? Let us understand the concept of induced EMF today. Students, actually induced EMF is actually the push of the electric charge which flows the electric current in the circuit. So let us write its definition first. It is basically, it's a push to the electric charges to flow into the circuit. अब ये चार्जेस को पुश करती है, ये जो एनर्जी है ये चार्जेस को पुश करती है कि वो सर्किट में फ्लो होना स्टार्ट हो जाती हैं. बट when we connect the bulb with the battery, students, have you seen that when we connect the bulb with the battery, the charges starts to flow from battery. But have you ever understood what is the force that induces that change to flow from the battery to the circuit? Let us write that it's EMF, and that is the force that pushes the electric charges to flow into the circuit. Now, induced EMF is denoted by E, symbol E, and that is how when a bulb is connected with the battery, it is lightened up because battery has energy, and that energy which battery is having is known as EMF, that drives the current in the circuit. So now let us understand how the EMF in the battery is calculated. Now, to see how much EMF, electromotive force, is present in the battery, we need a voltmeter to be connected with that battery. So we need voltmeter to be connected with the battery, and that is how EMF is calculated. Let us suppose we have connected a voltmeter with the battery. So it shows, sometime it shows 6 volt, sometime it shows 12 volt, sometime it shows 48 volt. Actually, this is the EMF that is present in the battery that drives the current. यही वो एनर्जी है, यही वो EMF है जो कि बैटरी से करंट को फ्लो करवाती है up to the circuit. So now electric field induces, it produces magnetic field. This is the point number 1, and point number 2, when magnetic field induces, it produces electric field. And these both fields, magnetic field and electric field, are perpendicular to each other. For say, if this is the electric field, so the magnetic field will be like this one. So if in blue it's electric field, so in black that is how the magnetic field is. These both fields are perpendicular to each other, and when electric field induces, it produces magnetic field, and when magnetic field induces, it produces electric field. So now let us study some of its laws. Now let us study case 1. In case 1, induced EMF is inversely proportional to the time in which it changes. That is how. Now let me show you how. First, say this is a coil and this is a magnet. Coil has some number of turns into it. First, say the number of turns in the coil is 100. And in example number 2, here is another coil and another magnet. First, say in this coil, the number of turns is 102, and here is a magnet. So when we get this magnet closer to the coil, it induces electric current, means EMF starts generating. But when we quickly take away this magnet from the coil, the voltage is quickly induces from 1 to, for say 5. But when, in this case, when we slowly get this magnet away from it, when we slowly get this magnet away from this coil, so the EMF will not that much induced as in the case 1. So maybe EMF induced is 1, 2 volt, 1 volt. Here, when we quickly take away the magnet from the coil, as it is quickly, the voltages or EMF is induced. So let us write the case number 1, that induced EMF is inversely proportional to time in which it changes. It means I'm here telling about the flux. Okay, so I will not write it. I'm writing flux. So in it, the induced EMF is inversely proportional to the time in which flux changes. So now here the flux changes very quickly. We'll take away this magnet very quickly. So the flux is changing in no time. So the more the EMF is generating in this case. Here the flux is changing slowly. Here in case number 1, flux is changing क्विकली, मीन्स इस मैग्नेट को हम जल्दी दूर कर रहे हैं यहां से, तो जो ईएमएफ जनरेट होगी, इंड्यूस होगी, वो ग्रेटर होगी. So the EMF induced will be greater. Here, when we take away this magnet slowly from the coil, so the EMF induced will be low or will be not that much as in the case 1. So here EMF induced will be low, as I told you here. So we'll write its mathematical equation that this E is inversely proportional to change in time. कि जितना ज़्यादा स्लोली हम इसको दूर करते जाएंगे उतनी कम ईएमएफ इंड्यूस होगी, और जितना ज़्यादा इसको इसके कॉइल से दूर करेंगे तो उतनी ज़्यादा ईएमएफ इंड्यूस होगी. Now let us discuss the case number 2, that induced EMF also depend upon the strength of the magnet. The more the strengthful is the magnet, the more the EMF induced is in it. Like, let me show you that in ferrite magnet it's a weak magnet, or in neodymium magnet it's a means strengthened magnet. So when the EMF is induced by the neodymium magnet, so it will be the higher induced EMF, and when the EMF is induced by that ferrite magnet, it will be the low EMF. So let me write the point number 2 is that induced EMF is directly proportional to the strength of the magnet. I am writing here too that induced EMF is directly proportional to the strength of magnet. Is in neodymium magnet the EMF is induced is high as compared to the ferrite magnet. So now let us discuss the case number 3. In case number 3, the induced EMF is directly proportional to the angle between the magnet and the coil. We'll write it as a cos theta, or this cos theta is actually the angle between the magnet and coil. ये मैं आपको समझा दूं कैसे. For say this is a coil and this is a magnet. So यहाँ पर जो EMF इंड्यूस होगी, ये जो सारी मैग्नेटिक फील्ड है ये क्रॉस कर जाएगी कॉइल से, तो EMF ज्यादा इंड्यूस होगी, EMF high. In other case, if we change the angle of the magnet, so all of the magnetic field does not pass from that coil, so the EMF induced will be low. Now in the fourth case, the induced EMF is directly proportional to the number of turns in the coil. So we'll write case number 4 that, sorry, we'll not write this E. That induced EMF is directly proportional to the number of turns in the coil. The more number of turns in the coil, the more the EMF is induced. Like here the number of turns is 100 and here the number of turns is 200. So the EMF induced in this case is high or higher. Okay, the more the number of turns, the more the EMF is induced. So I'm writing here too that induced EMF is directly proportional to number of turns in the coil. The more the number of turns, the more the EMF is induced. Let us write the case number 5. In case number 5, the EMF is directly proportional to the area. Like the induced EMF is directly proportional to the area of the coil. For say this is a coil and this is the coil. In both the cases, here higher EMF will be induced. So students, let us combine all the 5 cases. So when we combine all the 5 cases, so we'll write that induced EMF is directly proportional to NBA cos theta, and is proportional to the time. So we know that BA cos theta is equal to del phi. Okay, so we replace the value of BA cos theta with the del phi. So n del phi upon del t. So that is the mathematical equation of the induced EMF, and we'll write this is a Faraday's law of EMF. This is Faraday's law of EMF, and this is its mathematical equation. Hope students this topic is lot more cleared. Thank you.